Let's have sound. So yeah, anyways, that was just revision. So sorry about that. The first minute or so had no sound. That's probably what the person in chat is going to say. I can't hear you. Yeah, that's right. So I hope you can hear me now. I had my microphone turned off. So I was just saying about the fetch, decode, execute cycle. That is standard. So what I mean by that is that's the way all of our computers are designed nowadays. And that person there says, it's good now. That's good. Thanks, Sahar. Sahar is one of those people that has some quarantine issue or something like that. Can't come to class, so that's why we're doing the video. So you'll meet Sahar later. We'll look forward to that, I suppose. So in the corner, down at the bottom, we have a program. So this is like the first generation programming language. It's actually second generation programming language, because we say the first generation programming language was done with a soldering iron and wire, right? And so we had the electronic components, and we would join them up with wires to make a program. And then we got to these very, very simple commands, which we were able to address different parts of the memory by their address. Each of them had an individual address, and then we could do things with them, like put a number in there, then find that number, do something with it. And then we got these very sort of simple programs that, when I say simple, the program might not necessarily be simple, but the instructions were simple, but we'd have lots of instructions. So these programs could be very long, but each of the individual instructions were pretty simple. Does that make sense? There wasn't really much we could do. But the complexity would be sort of built into things like this jump. We could jump around in the program, go from this line of code to that line of code all over the place. Really, really hard to follow. And so, yeah, those early programmers, I take my hat off to them, because, you know, that was sort of really tricky stuff. You have to have a good memory. You have to be thinking quickly to sort of write that kind of code. But anyways, so our computers, we can thank this gentleman and a lot of those other gentlemen and ladies. There were some important ladies there that sort of gave us these ideas that we have developed into our computers. So here we have that represented. So you see this here, right? We got those big, big computers that are taking up a whole room. And we've got a simple way, or we have simple tools that we use to instruct them what to do. And so that would be like an assembler programming language. The assembler programming language would just have code like that: add R1, R2, R3, where R1, R2, R3 would be addresses would refer to addresses in the memory. Now these evolved into what we call variables in our next generation programming languages. So the way that would work is, as it mentions there, they'd use magnetic tape drives. Magnetic tape drive is a serial method of memory acquisition. What we mean by that is you have to start at the start of the tape and go to the end. So if there's something in the middle, we have to start at the start and spool through to the middle, kind of like the old cassette. And it wasn't a great way. It wasn't good for finding things, but it was okay for doing batch processing. What I mean by batch processing, you got 1,000 records and you want to do the same thing to all of them. Oh, that's great. Just put them on tape. Record 1, record 2, record 3, record 4. And, you know, very great for that. What's good about the tape? It's cheap. They still use cheap tapes for that kind of processing. Where, as I say, you know, at the end of the day in the bank, we want to see what is the account values of all of these, or we want to change them somehow, right? Most of it, that's kind of not a great example, because the way banks work now, it's all in real time, right? You go and spend 20 cents, not 20 cents, you know, 1 dirham, 1 real, whatever, you know, buying yourself a bottle of water. You know, that's recorded in your bank account now. Boom. You don't have to wait till the end of the day. But, you know, there might be something that you do at the end of the day. I don't know, you know, that maybe they add some points to some special system or something like that. At the end of the day, they could go through 1 million records all at once. You could do that on tape. That'd be nice. Or another thing you might use the tape for is a backup. You know, okay, so at the end of this day, we're going to store the records as of now. Now, why we would do a backup? Because maybe tomorrow the computer will crash. Then what do? Right? We lost all our data. But we can go and do a backup we can take the backup tape and load that back into the memory. And then we've got paper maybe of all the transactions that happened yesterday. We could reconstruct what happened, where we were before the crash. So we're always doing backups. Might be, depending on your system, might be daily, might be even more than that. But yeah, okay, so the old computers, They weren't using the tape just for backups. They were using it for all of their instructions. That's the best they could do, is just tape. Anyways, and they're big computers. Now, Grace Hopper, I believe she was an officer. So there you go. Wow, big officer, Rear Admiral. I mean, that's about as big an officer as you can get, right, in the Navy. So she had a pretty big job, and she was also a PhD, it seems. She invented the language which we call COBOL. And COBOL is an English-like language, which was a third-generation language. So I told you that assembler language is second generation. After that comes a third-generation language. They're a lot more natural language-like. It's kind of like talking to the computer, kind of. And COBOL programming language was. But having said that, one of the tests we do with computer languages to see how usable they are is we'll say, okay, say to the world, hello world. Get on your computer terminal and say hello world. In a COBOL program, that would take a minimum of about 55 lines of code to say hello world, because a COBOL program, you got to have like 5 different sections. You got a section where you put all your data. You got before you do the logic to sort of say something. Now, to give another example, the Python program language that you're going to use, if you wanted to say hello world on Python, what you would do is you would go to your terminal and you'd type print hello world. That's all it is in Python. So Python is a lot more usable than COBOL, I'd say. But COBOL programs, once you learned how to use them, that was I learned how to do COBOL programming in my degree when I studied. So they were still using it. I don't know if they're using it nowadays, but they were using it back in the 80s when I studied computing. So who was using it as banks, big businesses were using it. So it lasted from like about 1950s to at least the 80s. It wasn't a bad programming language. It was nice to work with. Integrated circuit. So last time we talked about a little bit, I think, about the transistor radios and transistors being miniaturized electronic gates. Yeah, so they're miniaturized like those tubes. So the next step from that was the integrated circuit. I think I mentioned integrated circuits as well, but I don't know. Basically, an integrated circuit is a silicon dioxide wafer on which we use we dope them. When I say dope them, you got pure silicon dioxide and you add to it an impurity in an exact amount. And the impurity is some other semi-metal oxide, like germanium oxide. And using that impurity, you can draw circuits. And those circuits have a semiconductor property to them. So that means by varying the electronic, varying the electrical properties, by varying the electricity, you can have switches between on and off. So 0 and 1. So you can have a bunch of electronic gates. So doing this, you could do the same thing with those bulbs, but we've miniaturized that so that we've got millions of them or billions of them in a very small space, so that you'd have to use an electron microscope to see them. So we're talking about at atomic size. You know what I mean by atomic size? Atoms and molecules. We're down to that sort of size, limiting what we're doing with our gates. So we've got gates that are just a few molecules wide. And so that meant that we could get a lot of computing on a very small space. So on a wafer. And the good thing, I don't know if I mentioned this to you before, but silicon dioxide is incredibly abundant. It's everywhere. The rocks are, well, not except for sedimentary rocks. Sedimentary rocks which were laid down at the bottom of the seafloor, they tend to be calcium carbonate type thing, right? But your typical rock that came out of a volcano once and was deposited that way, it's got a lot of silicon dioxide in it. Let's just put it that way. Silicon dioxide would be the main component. And so if you go down to the sand, and again, as I say, the sand, it could be a coral sand, in which case it would be sort of broken up bits of seashells. Well, that's not going to be silicon dioxide. But if it's a rock shell, if it's rocks, not shells, then it's mostly silicon dioxide. So silicon dioxide is most of the earth. We could talk about that a lot more if you wanted to. I don't know if you're interested, but silicon is a lighter compound than iron. And so when the earth was formed, the middle of the earth is mostly metals, iron, and other things. And the silicon dioxide was like a froth that floated to the top, and that was our mountains. and our rocks and stuff like that. So the outside of the Earth is mostly silicon dioxide and a few bits of other stuff. If you go down in the middle, you get a bit more heavier stuff, like iron and stuff like that. I don't know if you're interested in that. I don't know. I kind of found it interesting because my first degree was chemistry and I did a bit of earth science as well. Done a lot of stuff. I just like studying, I guess. So integrated chips been around for a while. They're really, really good. I think I mentioned it was part of the space program. So you think about it, if you got millions of gates in a chip, or billions of gates in a chip, you really made something light, which is powerful. And yeah, this is light and powerful. This is way more powerful than anything that went up in a spaceship in the 1970s. But yeah, of course, if they had spaceships now, and they do have spaceships now, they'll be using very small computers as well, which are very light. DRAM or Dram chips. Yeah, so these chips were made by this company, Intel. You've probably heard of them. If you open up your laptop case and look, there's a little sticker on there that says Intel i7 or something like that, or i3, depending on which one you've got. So Intel's still making chips for you. They used to make the chips in the United States, but that's become too expensive. So they started making them in Taiwan and Malaysia and not sure, maybe the Philippines, Thailand. So they make them in other countries, so it's cheaper. And of course, China wants to make them. And yeah, of course, Taiwan doesn't want China to make that. Anyway, so the politics is always in the background, right? So yeah, when we talk about chips and memory, we have to have a way of measuring it. And what you see here is we've got two ways of representing numbers. Do we? No. Maybe it's in the, yeah, here we do have two ways of representing numbers. We've got binary. We use binary for computers. Binary means the base is 2. So everything is 2 multiplied at some power. So like, what do I mean? We only have 2 numbers, right? We got 0 and 1, right? So you could have this number, that's the number 1, right? And then this is the number 2. And then this is the number 3, right? And then the number 4 is like that, right? That's 4, right? And then this is 5. And then this is 6. Yeah, you seen this kind of stuff before? I don't know if that's 6. 4, 6 should be like that. Sorry. 6. Yeah, because if it's got a 1 on the end, it's an odd number. So yeah, so 4, this is 5, this is 6. 6 is 110, right? And then 7 is going to be 111, and then 8 is going to be 100, right? So you get the idea. Now, if you look at this number here, 10, this number is what? This is actually this is just 1, but this is 2 to the 1, 2 to the power of 1. This is 2 to the power of 2, and this is 2 to the power of 3. Right, which is equal to the number 8. So 2 to the 3 is the number 8. Sorry, 2 to the 3 is equal to number 8. 2 to the 3 means 2 times 2 times 2. 2 to the 4 is the number 16. We'd write that like that, right? And then 2 to the 5 is the number 32. You get the idea, right? So 2 to the 50 or 2 to the 10 would be, 2 times 2 times 2 times 2 times, well, what does it say? 1024. 2 to the 10 is 1024. 2 to the 20 is, all right, so what they've done there is they've multiplied it 1024 by 1024. And so we got this special number, right? And as you keep going up, you actually lose it doesn't become a direct translation to the 10th power. Right, so 1000 is about 1024 is kind of like 1000, but it's not 1000, and so we can't say this is equal to 10 to the 3 because 10 to the 3 is 1000, right? So it's not exactly equal to, it's kind of near to, and so that's why this is also not exactly equal to 10 to the 6. It's kind of near to, but what it is it's 10 to the 1024 times 1024. So it's not exactly. And so we get these numbers that are kind of strange. You would have heard of that, right? Like, oh, I got this computer that's got a gig of RAM. A gig of RAM. Well, what's a gig of RAM? Well, it's not exactly 10 to the 12 or whatever it is, 10 to the 15, 10 to the 9. It's not exactly 10 to the 9. It's some number bigger than that. So we see this when I got a computer, it's got 16 gig flash drive. Well, 16 gig isn't exactly 16 billion bytes. It's 17 billion bytes. Why? Because of that 24 on the end of the 1,000 when we multiply it, right? So it's a little bit bigger than 1,000 that we start multiplying. I hope I didn't confuse you with that. Did I? I mean, base 2 versus base 10. It's a different deal. So in computing, we have to use base 2. Why? The zeros and the 1 represent our gateways. Our gateways are either open or closed. They're either true or false. And so we say that false is 0 and true is 1. And so everything is a 0 or a 1. We don't have 2, 3, 4, 5, 6, right? We can make those numbers up by combining these. Anyway, so you'll learn a bit more about that. Sometime in this course, you'll have to do binary to digital, binary to 10 base conversions. You'll have to do that, and also to hexadecimal. So I'll spend a lesson or two showing you how to do that. You'll probably also do that in your math class. So you do need to do that. Why would you need to do that? If you're going to do computer networking, you have to understand that, because we use that for getting our IP addresses for a network. Every network device has to have an IP address, and the IP address is based on a base 2 number. So you have to be able to do the conversions for it. That's one place you would use it. There may be other places too. Well, another thing is we use hexadecimal numbers in our program code. And so you have to be able to convert to hexadecimal. Hexadecimal is base 16. So you got base 2, base 10, base 16. Yeah, all right. Anyways, now Moore is an actual person. I guess he got a bit old because there he is there. I'm sure he looked a bit younger than that in 1968 when he founded the Intel company. So the Intel company I told you about, I think they were in Austin, Texas. They may have been in San Francisco. I'm not sure. I know that there was a lot of computer manufacturing stuff going on in Austin, Texas. So that's why I said I think it might be there, but they might not have been. So he observed. So that's what empirical means. Empirical is a word that scientists use all the time. When we say something is empirical, that just means that we have observed it, and that's how we came to our conclusions, as opposed to sitting at home or at our desk and creating a hypothesis and a theory and sort of doing some mathematics and saying this is what it is. Empirical means I actually looked at it. I did an experiment, and what I saw was that. And so he says that he actually looked at the costs of computing and the power of computing over time. And by looking at that, I observed that every 18 months, the power and complexity per dollar doubles. So bang for buck, or how much you get for a dollar, is doubled every 18 months. And that's a rule which is more or less still held true. Well, when I say more or less, how it actually goes, if you followed a curve, it would kind of be like, oh yeah, we're increasing our bang for buck up to here, and then we have a bit of a plateau. Then it increases, and then we have a bit of a plateau. And the plateaus sort of represent sort of, I guess you could say, engineering problems that are a bit too hard to beat at the moment. So we develop quickly, then we meet an engineering problem. It takes a while for the scientists to sort of come up and then collaborate with the engineers to solve that problem. Then we solve that problem, away we go, and then we reach another big problem. Now, my understanding is one of the big engineering problems that sort of kept the fact that, our processing speeds have been stuck around this 2.4 gigahertz for a while. My understanding is that's because we have an engineering sort of plateau there, which is, yeah, we could make faster processors, but they produce so much heat that the computers would not be usable. So we got to get some way of getting that heat out of them. We haven't really been able to do that very well. And so we're sort of stuck at this plateau. We make that processor go any faster, it's going to cook us. And probably some of you have had that happen to you, right? Sitting with the laptop on your legs and got burned, right? Fast processor, right? And we don't want to go any faster than that because it gets too hot and it actually starts melting the circuits, and then your computer don't work. Anybody have a computer have that happen to it? Yeah, me too. Then it just becomes a piece of junk, right? Because why? Oh, well, somebody was getting their legs burned And so they put a pillow on their legs, but the pillow was blocking the vents that were trying to blow the hot air out. So the hot air stayed in the computer and the computer burned up. Great. That kid was never invited back to my house again, I tell you what. that was also the last time I had an Apple computer. All right, so I should go back to this. The GUI, the graphical user interface. That's kind of what it looked like in like 1983 or 4 or something like that. The first people to come out with it was the Apple company. And so they came out with that Apple Mac and a box, Macintosh they call it, yeah, in a box. And the graphics weren't all that great, but it was way better than everything else. So I don't know what you know about Steve Jobs. He was the CEO of that company. He was a really smart guy, a tech, didn't have a degree in computing or anything, he's just a really smart guy. But he was also a bit of an artist. So that's why, you know, he's looking at the computers and he's like, you know, what is all this stuff? You know, why can't we do something nice? Why can't we have something that looks nice? It sounds nice, you know? Why does it have to be this, you know, engineering sort of, you know, unpleasant stuff? And so he wanted stuff that people could look at and work with. And so that was what sort of drove him to have the graphic user interface and also to have the sort of beautiful computers that they built and by them. And, you know, and so they focused a lot. I mean, they were the go-to computer. They may still be for you know, graphic artists and stuff like that. And so they really focused on having tools that people could use to draw things and, you know, to video editing. You know, people would use Mac computers, Apple's, because that's what they cared about. IBM sort of saw what Apple was doing and said, well, you know, we better do that. And so they came up with their own operating system that had a graphical user interface. And you can see that there where you got folders that you can see. And the idea there is you use a mouse and you click and you see what you want. And then Microsoft, Bill Gates' company, they came up with their own. And of course, most of us are using Bill Gates' operating system now, which is a lot better than it was when it first came out in 1980 something. The difference between Steve Jobs and Microsoft is that Microsoft is more open. Yeah, okay. So the open source thing, I mean, I guess what I'd say about that is you can have something which is fully open source. You could have a Linux thing, and Linux has a graphical user interface. I don't know why more people don't use it because it's free. Well, you know, nothing's free. You had to have some people develop it. But you are right that Microsoft has. I wouldn't say it's open source because we're paying for that. But the Microsoft thing, we pay for it when we buy the computer. But likewise, when you buy Apple, you're paying for their operating system. It gets shipped with it. But I think I know what you mean. For example, if you use an Apple product, if you want to get any new software, you have to go through the Apple Store. That's what you mean, right? And the Apple Store, they always charge you. Am I right? I don't know. Is there any free stuff on the Apple Store? I don't know. But for the software distribution, yeah, I would say that non-Apple is going to be more open, right? So for most of us now, we're using sort of Google. Google bought Android, the operating system, which most non-Apple phones is Android, and Google owns that. And so when you buy an Android product, they load Google on it, right? And so you have a Google account and you do everything through Google and use the Google Store. And a lot of stuff on there is free. There's probably free Apple stuff too, but yeah, and yeah, that's my experience too. Is you notice I'm not using an Apple. I don't use Apple stuff, and yeah, because I didn't want to have to pay for stuff through the Apple Store. But you know, if you got lots of money, I think Apple is kind of nice. You know, it's beautiful software and hardware. So yeah, and what I mean is it works and it works fast, right? You know, it seems to not sort of crash too much. I'm not going to say bad things about Apple, except as I said, my computer is not at Apple, and my phone is not Apple. So yeah. So we got these guys that we're kind of talking about. So there's Steve Jobs. May he rest in peace, because he's not with us anymore. Wozniak was his partner. And so Wozniak was actually the technical brains behind it. And Steve Jobs was sort of the concept person with the big ideas. Bill Gates, you might recognize. And his partner here is Paul Allen. Paul Allen succeeded Bill Gates as the CEO of Microsoft. Now, you look at those guys, and yeah, they're smart guys. I'm not sure that you would find them nice as friends. You know, what I understand is they had pretty sharp personalities. You know, Steve Jobs is pretty hard to work for. You know, he was really sort of a demanding boss. During the 1990s, a lot of guys didn't like, a lot of people didn't like Bill Gates because, you know, he was sort of, he had very hard business practices. In Australia, we'd say sharp business practices, which is another way of saying lying, cheating, and stealing. All right, you get the idea, right? Kind of like the Facebook people, right? You know, lying, cheating, and stealing, that's their sort of business practice. I won't say any more about that. You know what I mean, right? So, I mean, you know, they give us good products and we like it, but you might not like the way they did it. You know what I mean? But, you know, I guess that's business. Maybe that's why we're not in business, right? I don't know. All right, so here's some input devices. The mouse, the original mouse had this sort of roller thing. Original mouse we're talking about before Apple. Nowadays, our mice have got a light in them, and that's because the laser light is used because it's very sort of a bit more accurate and lasts longer than the roller balls. And so just by the light reflecting off, it can tell that it's moving in this direction and that direction. So that's a better mouse. Now this thing down here, that's nothing to do with it. I don't even know why it's in this slide. Okay, so what I mean by that is this thing here is a new topic, which is, so we worked on our user input. What about communicating with the rest of the world? Well, one way to communicate with the rest of the world is by some kind of wired connection. And we have a standard for that, which is the Ethernet connection. And our local area networks are all working with Ethernet connections. If you looked in the back of the computers that you got there, you'll see a blue wire. And that blue wire is an Ethernet cable. Now, blue is not standardized as the color for Ethernet cable. In some other classrooms, it's white, you know, and maybe it's black. Yeah, okay, so there's no color for it. It's blue in this room. But the Ethernet cable, how it is standardized is it's standardized to 8 wires that are twisted pairs. So 2 wires wrapped around each other. They're all insulated, and the twisting helps to stop having crosstalk or to get interference from outside devices. You can talk. You'll learn a bit about more of that if you do a computer networking and hardware course. So this is essential. So bringing it on to the next slide, the Ethernet. That was kind of essential to sort of build up networks. So by using cables, we can connect this computer to, well, this computer is going to be connected to the floor, and then that will go to a telecoms box somewhere. And some of the classrooms, they actually have the boxes. Somewhere on one of these classrooms is a box where these cables connect to, and then they connect to another box further down the hallway, and then that connects by fiber to our entrance point, which is in building 3. And then that has a point which Arito provides us with an internet connection. So we have a network here. All of our devices connect through communications equipment on every floor of the building. And then those all feed back to a central location in building 3, which then has cables coming from Arito to the outside world. Now that's a network. That's our network, right? And certain parts of that network are private to us as the college. So what I mean by that is we can sit here in our computer room, and we've got a network, and it's only ours. Nobody outside can use it unless we allow them to tunnel in using a thing called a VPN, a virtual private network. So why do we care about that? I can't believe I'm running out of time. Yeah, I think I got 10 minutes. I want to, oh, well, whatever. Okay, so the World Wide Web built out of this thing called the internet. So you have a network, which could be a network like this, a local area network. We call it a LAN, which is limited to a single location. And then you can connect that LAN, that network, to other networks. And when you do that, we can call that an internet network, an internetwork. And then we have this internetwork with a capital I, and that's the internet. And the internet is the internetwork which everybody connects to, because it goes all around the world. And that kind of started up in the, well, there's a lot of research in the 1960s. And then there was ARPANET. And as it says here, in 1990, what we got is we got a way of looking at data that was on that network in a way which was sort of pleasing and graphical. And that was this thing called Mosaic. And Mosaic uses HTTP, HTML, those two things. HTTP is the protocol that allows us to speak between different devices on the internet, and HTML is the programming language that makes our internet pages work. And so we got HTML, and then we had the internet proper that people could sort of surf around. The Mosaic was replaced by Netscape, which was eventually replaced by, we got Google Chrome and Fox. What is it? Firefox. And then there's these other ones, Opera, Safari, depending. So Safari is running on your Mac devices. Opera will run on both Mac and Windows based. And so will Firefox and Google. And of course, now we got the Microsoft is always trying to put their own one out there. And so what do we got for Microsoft? Does anybody use it? I don't know. Internet Explorer was replaced by, what is it? Microsoft who? Edge, that's the one. Edge, Microsoft Edge. Does anybody use it? Because I find, well, see, we're not using Microsoft here because D2L isn't compatible with it. So, I mean, so we do have some compatibility issues, right? But yeah, and the same with Internet Explorer. Microsoft does some things really well, but it seems that they're always sort of, I don't know, they're always in some other universe when it comes to the internet. Okay, so there's Bill Gates. Some people like him, some people hate him. Ex-wife is included in the second camp. But she's going to be very rich soon, but not as rich as the ex-wife of Jeff Bezos. Anyways, yeah. So yeah, smart guy. I don't know how nice he is, but he's a pretty smart guy. But okay, so he's smart, but he wasn't exactly knew everything, right? He said that the only amount of memory that we'd need would be 640K. So most of us are using a lot more memory than that on our computers. So it's pretty hard to predict things. Now these guys, another couple of really smart guys. You guys know what these guys did? You heard of Google, right? Okay, so when they first wrote it, they called it backrub or something, right? What did they call it? Yeah, backrub. All right, so those guys were at the Stanford University. I don't know if you're familiar with that. Stanford University is in the San Francisco Bay Area. And what happens at Stanford University is the university has a lot of contacts with a lot of really rich people. And those rich people go to Stanford University looking for smart students that have good ideas, and then they're going to give them some money, and then they're going to have a startup, and it's going to make a lot of money, and those rich people are going to get even richer. So that's the idea of Stanford University, that they have and so we have a lot of businesses coming out of it. And so one of those businesses was Google. So these smart people, these smart guys, they came up with this thing, and then they got a bunch of money from a bunch of rich people that lived around there, and they got their company going, and now they're really, really rich. And those rich people that helped them out are even richer. So what a good idea that was. Now, apparently, Google is a word that actually means something. It means the number 1 with 100 zeros after it. That's a Google. And so why would that be important? Because it's a really, really big number. And their idea was there's a lot of information in the world, and we want to give everybody an access to it. So we're going to have a search engine. And so the really big number meant the amount of facts that people would have access to. So, I mean, you can go and Google your own name, right? And if anything's on somewhere on the internet and it hasn't been sort of hidden, you can find it. Other people could Google your name too, I suppose. Yeah, so they're worth a lot of money, trillions of dollars. Can you imagine that? Trillions of dollars. So, I mean, at one point, I think it was the richest company in the world. And then Jeff Bezos, Amazon became the richest company in the world. And then more recently, Elon Musk's, he's got a bunch of companies, right? So he's got Tesla and SpaceX. And so, I mean, all that together has become the richest thing in the world. And good for Elon Musk. Yeah. All right. So there's some history. It's cool. All of this has happened, right? So most of you guys were born around here, I suppose, around the 2000 mark. So a lot of stuff's happened since then, right? YouTube only started in 2005, since you were born. And it's a big thing, right? A lot of searches on YouTube. Whenever I break anything on my motorcycles, I go to YouTube and see how to fix it, right? If you want to learn how to do calculus because you missed one of the classes, you could go to YouTube and search. You'll find lots of people there showing you how to do calculus. Likewise, you could have somebody teach you how to do Python just by doing a search on YouTube. There's a lot of stuff on YouTube. And yeah, Nintendo, Apple, blah, blah, blah. Okay, so can you guess? We're all about done this one. All right, so who's that? Steve Jobs, right? Yeah, okay. What did he do? Apple. Babbage. We're not really guessing because the answer's there, right? Sorry. If I did the PowerPoint, then you'd have to guess. So well, I'm not making you guess, but so this is just really a revision. There's that Turing guy, code breaker. There's that lady, Dr. Rear Admiral Grace Murray Hopper, who developed COBOL programming language, which was a really big language for 30 or 40 years for business. And going even further back, Blaise Pascal, who was a philosopher, mathematician, and developer of a computer, a sort of a physical, a mechanical computer. All right, so I'm going to stop that now, I hope. How do I get out of that? That one. Very good. So what I'm going to do is the next, do you want to take a break now? And then we'll, so I'll close this off and then we'll open up the next one. And then I'll only be a minute. Okay, a couple minutes. So why don't I do that? I'm just going to stop this. I'll stop the recording and